Hi, my name is Mark Case, and I'm the Science and Motion Director at Lehigh Carbon Community College. Today, we're going to explore a lab where we're going to study the evaporation of liquids and try to relate that to their intermolecular forces that are holding them together. So it'll be almost exciting as watching paint dry. We're going to do an analysis where we're going to try to figure out different types of organic substances, things that are carbon-based structured and have oxygen, carbon, hydrogen, other atoms that might be bound onto it. And to study this, we're going to look at how much the temperature drops as these liquids begin to evaporate. So in order to show you how we're going to be exploring this, I'm going to minimize myself and share my screen with you. And you will see that right now there's a temperature probe here. This is a Go Direct temperature sensor, which has a built-in Bluetooth that's added onto it. And I have opened up the file of a program called graphical analysis. So I am going to do sensor data collection. And what this will do is it will be able to link via Bluetooth, or you could do it also with a USB cable connection. But it's be communicating the information that's going to be collected by this sensor, and that will show up on our individual screen. Now, right now I'm displaying just the graph, but up here in the upper right-hand corner, I have an option to change this. And let's throw a data table in there if we want, or we can also throw a meter on there. There's always going to be a small meter that would show up down at the bottom of the screen, but sometimes that's a little bit difficult to be able to see that as the experiment is progressing. The experiment itself is already by default setting it up so that they're assuming your variable that's going to be changing and being dependent on the time is going to be your temperature value. And then the independent variable is going to be the time itself. And it sets it up so that it will do readings for 3 minutes to store the liquid and keep it in contact with the end of the sensor. What I need to do is take a paper towel and just wrap it around the end of the probe. So I'll twist that around and then take just a twist tie from a bread wrapper or anywhere else you can get one that will be able to do. And now we're ready to collect our data. So I'm going to get nail polish that I have available, acetone. And I'm going to get just a small amount into a thin stem pipette. These thin stem pipettes will hold a little over 3 milliliters. There's actually a line on here which would give you about 1 milliliter. So I'm going to fill it up just to about that line. I'll close up my bottle here right away while we're ready to go. And I'm going to start data collection before I add it onto the paper towel, because I want to get a starting point of what's the initial temperature value. Now, by default, it's going to set it up so that the temperature is at 50 degrees as our starting point. But when I hit the collect button, you see the temperature is really about 25.2, and our graph begins to display that down here at the end. If I want to, I can double click on the graph. And what that will do is it'll rescale that for your setup, and it will still keep running for that whole time period. I'm ready to begin adding my drops onto it. I'm going to add it slowly at first so that it doesn't spill all over the table. And as I'm adding it on, you can see that the temperature is taking a dive. It's dropping relatively rapidly. We're down to 22 degrees in 45 seconds. So that's a fairly significant change that's taking place. You can see that it's continuing to go pretty much straight down in the process. And it will continue to rescale as it runs through the rest of the experiment. But you see that in a matter of 1 minute, we went from where we were somewhere around 22 degrees, 24 degrees to about 16 degrees. So you're looking at a drop in temperature that's very dramatic. And it has to do with the fact that the attractive forces between one of the acetone molecules for its neighboring molecules is going to be fairly minimal. The structure of the acetone, if you look at the arrangement of the atoms, there are 3 carbon atoms, all connected together in a row. The end 2 carbon atoms are going to have 3 hydrogens bound onto them. So carbon can form 4 bonds. Therefore, you end up with carbon with 3 hydrogens on the end and then hooked onto the carbon in the middle. So you have 2 of those on either side, like bookends. The center carbon has only the 2 single bonds to its neighbors. So the oxygen comes in and forms a double bond between those. Take a moment and draw that structure. It's called a Lewis structure while we're waiting for our temperature to finally stabilize, or we'll get to 180 degrees and the data collection will stop. You can see that the curve at this point is no longer going straight down, but it's starting to flatten out. Part of this is because of the fact that it's reaching the stage where it's at its maximum temperature change that you're going to get. Also, if you have it evaporate quickly enough, what will happen is it will begin to warm back up to room temperature, but you should be able to see that at the end of the curve if that happened, because it would start going back up. So we're not going to reach that particular point. So we're almost at 180. So our first run has stopped. We have the acetone that we now have been taking a look at. What I could do is come over on the graph itself and just click somewhere along where it was first, just the temperature probe without any liquid on there. And we can see that our temperature started out at about 25 degrees or so, somewhere in that particular area. You could drag across that area and highlight that if you wanted to. And down in the bottom left-hand corner, you could actually add on their statistics if it wasn't very linear, but it was more irregular. And you can get an average, the value called the mean. It shows that it's 25.033 for all those data points. So if necessary, you could use statistics to get that particular region. I can also take a look at the difference between the two. So if I just take the entire graph and not just the beginning and say, show me the statistics, it's going to give me what is the change that occurred in my temperature. So the delta Y, the change from my highest temperature to my lowest temperature, is a value of about 28.9. It's the 22.9. It's about 22.866. You can see here on the scale. So you could use that also as a gauge of evaporation, how quickly it faded in temperature and dropped off, and what was the maximum difference that occurred. There's a third way that you can take a look at this change, and that would be that during this portion where it was dropping, and it was fairly linear before it starts to bend off of that straight line and starts flattening out. So maybe in the first minute or so, not much longer than that, what you can do is you can do a curve fit. So down under here, using the graph tools once more, say apply a curve fit. And for that, I'm going to say, give me the linear fit for that particular region. I'll move this up out of the way here a little bit. And that just gives you a slope. That's the most important part. We're looking at the M in the Y equals mx plus b. You will see that it's a negative 0.26. So it drops down 0.26 degrees every second in terms of that relationship. So you can write that down as a rate of cooling. Now, as a comparison, since I have that value, I can do another trial. I want to be able to remember what this one was. So up here where it says data set 1, if you click on the 3 dots that are horizontal up there, it lets you rename that data set. And I'm going to make sure that I put in that was acetone, so that later on, when I have a whole bunch of different liquids that I've tested, I will be able to find out what that one was. I'm going to run a second trial. I have a new paper towel on my temperature probe all ready to go. The temperature is warmed back up to room temperature or so. It's about 21.9 degrees. It was a little warmer with the acetone because I was holding the end when I put the paper towel on. So for this one, what I'm going to do is use a second liquid that you might have around your house. And that, of course, depends on, your ability to be able to find this. But we're going to be using isopropyl alcohol. This is also called 2-propanol. It has a 3-carbon chain, just like the acetone has 3 carbons in a row. But the difference is that instead of having a double bonded oxygen on the center carbon, it has a bond to an oxygen that is then also the oxygen's attached to a hydrogen. So it's an alcohol. We call that an alcohol setup. It's tough to find because it's useful as a disinfectant. What I could do is I could make a prediction about how much the alcohol is going to evaporate relative to the rate at which the acetone did. So this is where you start talking about the intermolecular forces. In any molecule or any atom or any ion, you have electrons that are in that atom, and that electron creates a negative cloud. As one of those molecules or atoms approach a neighbor, its electron cloud repels that cloud of the neighbor because they're both negatively charged. So you end up with a slight imbalance of charge within that molecule. And then these induced dipoles, they're called, you have a buildup of charge temporary between the two molecules. They will start to attract each other. So that name is called dispersion interaction or dispersion forces as a attractive force that are holding them together. Well, here we have the OH different than the carbon double bonded to the oxygen. So they're going to have slightly different attractive forces there. One of them is going to have just dipole-dipole forces. The other one will have dipole-dipole forces and what's called hydrogen bonding, which is a type of intermolecular attraction. So the propanol actually has a little bit extra bonding with that OH group that's on there. So I think it's going to, what do you think, evaporate faster or slower? I can add a prediction where I think that's going to go. So if I think it has stronger attractions, that means it's going to start, up here where the initial value is. My temperature is around 22 or so. It's going to be somewhere in this area. And then if it has stronger attractions, does that end up dropping like this? So it ends up going down lower? Or does that end up where it starts out like this and we end up having a situation where it's going to end up at a higher value? So when we start adding it, it's still going to begin to evaporate, but maybe not as fast, and then end up somewhere in this area. So if I put a prediction on there, let's see what happens. I don't know. Your guess is as good as mine, so let's see what we get. So I started it. I'm seeing the graph come across. So I was pretty close on my starting point, right around 22 degrees. Let me add the propanol. And I add that on there. The paper towel is supposed to keep the liquid from dripping off all over the place, but it's going to run a little bit. And so far, you can see that my prediction is a little bit off compared to the rate at which it's cooling down. But make sure that I've saturated the paper towel. So again, about 1 milliliter is what I'm using in each case. And I don't see where my first graph went to. Well, on the y-axis, it's not gone. It's just not being highlighted. So I can click, and just as a comparison, I can see, oh, definitely, this is going at a much slower rate of evaporation than that of the acetone was.